Okay, continuing on page 2 of your packet, we've got a couple different things we need to talk about that really goes along with the coordinate system that we talked about earlier this year. One of the things that we're going to talk about is a line or axis that will separate a shape into parts that are congruent but face each other. Okay, for example, you could see that if we folded along this axis, these two parts of this shape would fold exactly on top of each other. This line is called a line of symmetry. Okay, so a line of symmetry. Now, if you, for example, talked about a rectangle, you could fold along this line and the two parts would overlap. You could fold along this line and they would overlap. But if you fold it along the diagonal, that is not a line of symmetry because this part would be here and this part would be here, and so they wouldn't fold completely on top of each other. So this rectangle would have what's called two lines of symmetry. If you had a shape that looked like this is called a parallelogram. We're going to talk about here in just a minute. If you were to fold here, you could see that those corners wouldn't fold on top of each other. And if you were to fold along the diagonal, this part would come here and this part would come here, so they wouldn't fold on top of each other. So this parallelogram would have no lines of symmetry. And then you have a shape like this, a circle. It doesn't matter where you draw that line of symmetry, that circle is going to fold completely on top of each other. So this would have an infinite number of lines of symmetry. So there's a lot of different opportunities to have a line of symmetry or none at all. It just depends on if the shape folds exactly on top of the corresponding part. Now, if you have a shape that has been flipped along an axis, and for example, the parts are corresponding, that's what this is talking about. In other words, the distance to this axis and the distance to this axis, if they are exactly the same, what this is called a reflection. So if a shape or polygon has been reflected across an axis, it's like a flip. It's like you looking in the mirror. You can see your image across an axis. That axis is the mirror. And so you can see that the point of this triangle and the point of this triangle are the same distance away from that y-axis. So you'll be able to work on that in one of your IXLs here in a few days. When you have a shape that has turned 90 degrees or 180 or any degree along an axis, so you can see that this shape, this point, now has turned from north to east, so it's been turned 90 degrees. What that's called, if a shape spins along an axis, that's called a rotation, just like our globe rotates. Well, instead of it spinning, the shape has rotated. So this polygon has rotated 90 degrees to the right. That's what that's talking about. So a rotation or rotate. Now, this is one you might have probably never heard of before, but if you notice, this is just like pushing a shape along a line. Your car, so for example, if you drive your car down the street, the location has changed, but the direction of your car, in other words, your car hasn't spun around. The front of your car is still going in the same direction, just like this shape, when it slides along an axis. What this is called, this is something in math called a translation. So if something has translated, it just slid along an axis. So you've moved this shape across that axis to that location. And so it didn't rotate and it didn't flip. It's like you pushing a little matchbox car. That's what a translation is. So easy way to remember it, a reflection is like a flip. The shape's flipped across that axis. A rotation, it's spun across that axis. And then a translation, it slid across that axis. Those are going to be some buzzwords that you need to remember. So a flip, a spin, and a slide. And then finally, down here at the bottom, we need to talk about this word adjacent. So if you're standing adjacent to your friend, you're not abiding by that 6-foot mandated social distancing. You're next to. So adjacent means that you need to be next to. If you're not adjacent, then you're not next to. It's not the house next door, it's 2 doors down. So non-adjacent is not next to. That's just all the word adjacent means, is next to. So what this says, an interior, we just talked about that, an interior line segment that connects 2 points that are not next to each other, vertices is a point, of a polygon, but it can't be an edge, it can't be a side. Here's what this means. Here's one vertex, here's another vertex. If I connected those two, that is not an edge, and it goes through the inside. When that happens, that's called a diagonal. And that makes sense. That goes across that shape diagonally. Well, it also has a diagonal if I were to connect these 2 points. So this shape has 2 diagonals. Now, if I connect these two, first of all, they are adjacent points because they're next to each other, so that would take out that definition. Also, if I did happen to connect these two, that's considered an edge or a side, and a diagonal can't be a side. So it can't be connecting points that are next to each other, and it can't be a side. Well, this is going to be an important concept that you're going to be talking about a little later. This is actually a sequence that will be important a little bit later on in geometry, but we're just going to get to it right now. If you think about this triangle, and we were trying to find the diagonals of this triangle, well, every single one of the vertices of this triangle are adjacent to one another. So any one of the vertices that we tried to connect would be an edge. So this triangle actually has 0 diagonals. Now, any 4-sided polygon, doesn't matter what 4-sided polygon you draw, you can connect these non-adjacent vertices, and so a 4-sided polygon is going to have 2 diagonals. Now, we'll talk a little bit more about these 5-sided in the next video, but you can see that this 5-sided polygon has 5 vertices. So I couldn't connect these two because that would be an edge, and they're also adjacent, but I can connect these two. Those aren't next to each other and they go through the inside. Here's a second diagonal. Here's a third diagonal, a fourth diagonal, and a fifth diagonal. So you can see that the diagonals of that 5-sided polygon created a star there. So this would have 5 diagonals. Then you have this 6-sided polygon. So if you look at these 6 vertices, these sets would be adjacent, but that's 2 non-adjacent vertices that I could connect. Here's a second set. Here's a third set. 4th, 5th, 6th, 7th, 8th, and 9th. So a 6-sided polygon would have 9 diagonals. Well, I don't want to keep drawing these diagonals because you can see as we add a side, look how many more diagonals we get. So I'm going to look for a pattern here, and maybe something might ring a bell with you guys and girls. So I'm going to give you just a second to look at this. Okay, hopefully you can see that once I added a side, that added 2 diagonals. I added another side, now that created 3 more diagonals. I added a new side, that created 4 new diagonals. So now if I add another side, which is a 7-sided polygon, it's going to add 5 diagonals. So you can draw those if you want to, but there's going to be 14 diagonals inside that 7-sided polygon. Stop sign, or an 8-sided polygon, I'm going to add 6 new diagonals because I added a side, which is 20. I'm going to add another side to make a 9-sided polygon. Well, you can see if I added a side, that's going to add 7 new diagonals. And then a 10-sided polygon would have 35 diagonals, and that's going to be something that we're going to be talking about a little later, this pattern that you see here. And we're going to go into that a little deeper later on in this unit. Round 3 coming up.